Okay, I am now going to um, do a simulation of what our in-class activity might have turned up, but using a computer to do the simulation instead of doing it by hand with cards. So what I'm going to do is I'm going to use some basic R commands to kind of create the simulation. And this might have a lot of similarity to lab 4. So yeah. So something I'm going to do, and because I'm going to use R not just as like a fancy calculator, but a little bit beyond that. So I just swapped my console and my note thing so that the console will be further up for you guys to be able to see it better. I'm going to write some things down here, and then I'm going to press Control Enter to run them up in the top. So I'm going to use this R command called rep135. And if you see that, it repeats. So rep is repeat. So it repeats 1 35 times. Okay. And then let's see. I'm going to do okay. Then I'm going to do like C. I do C of, C is for concatenate. So rep 135 and rep 0 13. If I run that, then I create 35 ones and 13 zeros. So my ones correspond to number cards. My zeros correspond to face cards. And so back in like the study, my ones correspond to people who were promoted, and my zeros correspond to people who are not promoted. And from the get-go, I can't tell if the ones are males or females because we're assuming the null hypothesis for the simulation. We're assuming there's no difference between male and female promotion. Then I'm going to actually kind of call that something. I'm going to call it the deck. Okay. And then I'm going to take a sample. And so call it SAM. Will be there's this function called sample, which does, it looks at a list of things, and you can take out 24 of them randomly. Okay. So then let's write what SAM. SAM is just a random sample of ones and zeros. So we've got 1, 1, 1, 0, 1, 1, 1, so on. Okay. So then that's like, let's say that's my pile of male, the cards I dealt to them for male. Then really what I want to do is I want to count them up. Okay. So then I'm going to use a function called sum. And I might rename this then to be, I'll call it M promoted. Okay. So then M promoted is going to be, in this case, 19. Okay. So then the other hand would have been the females that were promoted. And I'm not going to do sample again because it's dependent on where I dealt the males. So it would be 35 minus male promoted. Okay. So then, F promoted, in our case, is 16. Okay. So then what I want to do is I want to look at the difference of proportions. So then diff will equal the male promotions divided by 24 minus the female promotions divided by 24. Okay. So then diff is, in this case, it's 12.5%. Okay. Now remember that in the actual study, the difference was 30%. And so with random chance, I got 12.5%. So what we're going to do is we're going to do this many times and try to see how often we get a difference of 30%. Okay, so I could do all those lines of code many, many times and like write them down somewhere, or I could use the power of the computer to do that for me. So I'm going to do a little bit of coding that you don't really need to know as much. This is just for the purpose of doing simulations. Our course is not really about doing simulations. We're using simulations to teach you something about statistics. So how many simulations should I do? I'll start off with doing 5 simulations. And then I'll do for I in 1 to 5. So this 1 to 5 thing, if you do 1 to 5, it gives you the numbers 1 through 5. So then for, I'll do, copy this stuff right here. Okay, so I'm gonna like do that 5 times, and then I need somewhere to store the results. So I'll call that differences. That'll be a list of things, list of zeros of length 5, and then I'll replace the zeros with the numbers as we do them. So then I'll say differences I, and the bracket I gives me like the ith one in there, equals diff. Okay. So then if I do that, then, oh dear. Oh, because I did a tab and it put in a function. Okay. There we go. And so then we can look at differences. Okay, so some sample differences would be, the first one was 12.5%, and then it was 20.8%, and then it was 4.1%, and then and there's, you know, there could be negative too. It'd be more females promoted than males if we're doing it randomly, and so on and so forth. Okay, well, then let's not just do it 5 times. If I'm doing it with cards, I'm kind of limited by time, but a computer can do things much faster than I can. So let's do it. That shouldn't be 5, that should be n right there. So that if I just change, and that should be n. So then if I just change n to be, instead of 5, I could do 1,000 or maybe million. All right, so then if I do that, and it's already done. No, it's thinking. Million might have been a little bit big. Okay, come on, little guy. Million simulations are done. Okay, so then let's create a histogram of the of our simulations, and then let's put in a line at the difference that we observed. So so I'm going to do ggplot. Yeah, I should probably bring that in the tidyverse. Okay. Yep, make sure got the tidyverse going on. All right, so then ggplot, and then AES. Now, normally when we do ggplot, we have a data frame, and here I just have a vector. So I don't put anything for data. I just put an AES x equals differences. Okay. Plus geom histogram. I think it'd be even better if it had dot histogram. I don't remember how to do it off the top of my head. So you guys can watch me try to remember, or I could just do it this way. Let's try to do a dot histogram. Okay. Plus geom dot plot. And since I don't remember how to do it, I'll just do question mark geom dot plot. And that brings up my help file over here. And then data, position, stack ratio, dot size, stack groups. Bin width. I want histodot. Basic approaches, not dot density. I want histodot. Okay, so where does it say histodot? Position, data, mapping, frame function. Okay, I don't see it there. So geom dot plot, color, bin width max width for each bin if method is dot density width of each bin. All right, so method. Is method in there? Okay. Method equals histodot. Okay. Right. So here, let's do that and see what happens. And we'll see if you can. Okay. All right. It doesn't like that it's just a vector. So let's make it data frame. So then, so I could do differences, do data frame. And here I'm piping. So I'm starting with the vector of differences, make it a data frame, and then apply ggplot, where x equals differences. In fact, if I don't know what's going on, what it's going to look like, I just put in a little view here and then put that down there and run it. So then, yeah. Okay. Okay. So then x equals, so then what if I did like x d equals dot. All right, so now I have a name for a little d. All right, so then when you're doing piping, period can refer to the previous thing. So then I've see me figure stuff out on the go here. So then x equals d. And then let's see if that works. Okay, it's thinking. Shouldn't have done a million. A million was too much. Should have slowed it down a bit. Let's, in the future, let's take off some zeros there. Okay, and yeah, I mean, that's this is the problem with doing it like that. So let's rerun everything with only 10,000. Okay, it's still a lot. And so I need to go back to the help file. And how do I adjust the bin width stacker equals scale watt continuous? Okay. Okay. So maybe if I had scale y continuous. And if this doesn't work, then I'm gonna pause this video and figure it out. It's too much to be recording while I'm doing this. All right. Okay, I'm back. I just wanted to create a plot that was similar to your homework problems, and that ended up being harder than I thought. You never have to do that for your homework. I just wanted to make something that looks similar to your homework. So let's get started. So where I changed things was I'm going to do only 200, which is a similar size, simulation size to a lot of your homework problems. I'm going to set the seed. That's a thing to make, like when you make random numbers, if you want to make it reproducible so that everyone else gets the same random numbers you did, you can do that. And then I'm going to say differences is that, do the for statement, then I'm going to make this plot. So then let's zoom in on the plot. So, oh boy. Oh boy, we're all over the place. So anyway, here, this is kind of a thing you might see in homework problems probably from chapter 4, perhaps, or maybe from this section. Yeah, so from this section, you might see some homework problems that give you this histogram of a simulation. And they ask you to kind of determine how unlikely this thing was. So remember what our study showed. Our study showed a 30 percentage point difference. So these are all the different differences we got from random chance. Most of them are around 0. And there's some out here, like within 20% difference, 20 percentage point difference is pretty common. And then out here, that's like the 30 percentage point difference, like what we saw. So there's 1, 2, 3 over here, 1, 2, 3, 4, 5, 6, 7, 8 over there. And I think we should, when we talk about this later in the slides, we should count both sides. It's always best to do both sides. It removes some of the bias of you. So if you go into this, sorry about the train. If you go into this thinking like, oh, only women would be discriminated against, then you have a bias. It might be right, it might be wrong, you don't know. But if you just go like, let's just find all the discrimination. Like, what's the chance of any sort of discrimination, male or female discrimination? So we'll count up both sides. So 3 and what did I say? 11, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so 11 out of, I did 200 simulations. Okay, so 11 out of 200 is 0.055, which means it is, according to our simulation, it is the study showing a 30 percentage point difference between men and women being promoted. There's only a 5.5% chance of that happening according to random variability. Okay, and then this might even be a little bit high. I bet if we did our simulation a little bit bigger, we might get an even lower number, I think. That's how it was set up. So let's go back to those slides then. So, do the results of the simulation you just ran provide convincing evidence of gender discrimination against women, i.e. dependence between gender and promotion decisions? And so answer A is no, the data do not provide convincing evidence for the alternative hypothesis. Therefore, we can't reject the null hypothesis of independence because gender and promotion decisions. The observed difference between the two proportions is due to chance. And then answer B, yes, the data provide convincing evidence of the alternative hypothesis of gender discrimination against women in promotion decisions. The observed difference between the two proportions is due to a real effect of gender. And so B is the most likely thing here, but we haven't proved it. We've just shown that it's unlikely. Okay? So here is an example from the book. They did their simulation, and they came up with this. They have much less than 11 going on there. And so in their case, they have just 1, 2, and 3, 4, 5. 5 out of 200, which is way below 5%. It's like 2.5%. And usually like 5%, we'll talk about this later, 5% is usually a good cutoff for, that seems like below 5%, it's like, that's pretty unlikely. Okay, so the p-value is, this is super important. You should put this in your notes. The p-value is the probability that we would get results this extreme, assuming the null hypothesis is true. Okay? Our simulation is a rough way of calculating this probability. Okay? So the p-value is not, it's not the probability that we're right or wrong or whatever. It's the probability of getting something this extreme, in our case, like 30% or more difference between the proportions in one way or the other. Okay, so number of times differences is greater than 29.2 divided by total number of simulations. Okay, that's how we do it with simulations. There's going to be some more mathematical ways we'll learn how to do this later. So looking at the plot, we can count the right or count both sides. So the p-value, if you only look at the right, is 0.02. Although theirs is 100, not 200. Okay. So simulation. So we say that the data provides statistically significant evidence against the null hypothesis if the p-value is less than some reference value. And usually it's 0.05. You're supposed to just set it before you do it. Okay. You don't like wiggle around and say, oh, it's low. You just kind of set before you do the experiment. You say, we're going to use a 5% significance value. There's a video, you should check it out. It kind of is a great way of explaining why 5% is a good number. It's not a perfect number, but it's just, we got to draw the line somewhere. Okay, not even scientists can easily explain the p-value. This is also a great video about the p-value, and then I'm going to go to the XKCD thing because I think it's worth it. So you can see here, let's zoom in. Somebody says, jelly beans cause acne. Scientists, investigate. We found no link between jelly beans and acne. P is greater than 0.05. That settles that. Here it's only a certain color that causes it. Scientists. All right, so we found no link between purple, no link between brown, no link between pink, no link between blue, no link between teal, no link between salmon, no link between red, no link between turquoise, no link between magenta, no link between yellow. We found no link between gray, no link between tan, no link between cyan. We found a link between green and acne. Whoa! We found no link between mauve, no link between beige, no link between lilac, no link between black, no link between peach, and no link between orange. News! Green jelly beans cause acne. Okay, why is that bad? How many different colors did they try? There's 5, 10, 15, 20, right? 5% is 1 out of 20. So if there's nothing related, you'd expect to get a false positive 1 out of 20 times. So if you test 20 colors, it's likely that one of them you'll just get a false positive. So always be careful with stuff like that. All right, let's go back to our slide here. P-value is so important that there's this beautiful haiku. Let me move this so it's out of the way. Little p-value, what are you trying to say? Of significance. Okay, so decision errors. So if the null hypothesis is true and we do not reject the null hypothesis, then that's good. If the alternative hypothesis is true and we reject the null hypothesis, that's also good. If the null hypothesis is true, but we reject it, that's a type 1 error. And there's another good name for that. So if you think something's going on, but it's not really going on, then it's a false positive. So positive means like something's going on. And then type 2 error would be a false negative. Okay, So a great example for this is pregnancy tests. So type 1 error is a false positive. It's like telling someone they're pregnant when they're definitely not pregnant. Type 2 error is a false negative. Someone is pregnant, but you tell them you're not pregnant. And that's because the normal state of human affairs is not being pregnant. And so being pregnant is something unusual. So that makes it the alternative hypothesis. And so then that makes the difference between the type 1 and type 2 errors. All right, if the null hypothesis is that a person is innocent and the alternative hypothesis is that he or she is guilty, then what is the type 1 error? What is the type 2 error? Stop and think about that, okay? I'm gonna pause this while the fire engine goes by. Oh, they're passed, all right. Okay, I think the fire engines are gone. Anyway, decision errors. If the null hypothesis is that a person is innocent and the alternative hypothesis is that he or she is guilty, then what is the type 1 error? What is the type 2 error? Well, type 1 error is an innocent person is thrown in jail. The type 2 error is that a guilty person goes free. And the way we've designed our hypothesis tests is similar to the way that the court system is designed in America, is that an innocent person being thrown in jail is worse, in our opinion, than a guilty person going free. So you change the significance level based on which error you think is worse. So two-sided hypothesis test. So in our gender discrimination case study, we never considered if men might be discriminated against. Well, I did, but in my slides I didn't. All right, so most of the time, our alternative hypothesis should be two-sided, aware of both extremes. This helps prevent confirmation bias, which is when you're unable to kind of think about how it could have been the opposite way of what you assumed. Okay, so to compute p-value for a two-sided hypothesis test, first compute the p-value for one tail, and then it should be less than 50%. If it isn't, you're computing the wrong side. Then double that value. So for instance, compute the p-value for one tail, and then kind of double the value to get the other tail. All right, so this is an example of where in class we would have gotten in groups of 2 to 4 people. We would have done exercise 225 on page 75 together. I think I will pause and do that now.